All right, let me get set here. Okay, yesterday we worked on permutations, where the order of the objects made a difference. Today we're going to look at the other side of the coin. If you remember, these are going to be combinations. So, section 3-4, day 2. So when the order of the objects does not matter. And to say it does not matter, when you switch two things, you do not get a new outcome. Okay, that's when we have a combination. So if I switch and it's not a new outcome, that's a combination. If I switch and it is a new outcome, then it's a permutation. So I say does not matter. I'm going for, it's called a combination. And we have our NCR button on the calculator, which means if I've got n total objects and I'm choosing r of them, the total number of ways to do that is, well, here's what's built in. Here's the math behind it. N factorial over n minus r factorial divided by r factorial. You won't have to do it by hand. We're just going to use the NCR button. So let's take a look. We're just going to do a bunch of examples today. There we go, example 1. Let's say the track team has 20 people. And we are going to pick a captain for the team and an equipment manager. Okay, so captain and equipment manager. Does the order matter here? So, for instance, if I pick Jake to be the captain and Dan to be the equipment manager, if I switch them around, is that a new outcome? Well, it absolutely is. Dan's now the captain and Jake's the equipment manager, so that is something brand new with the same two people. So this is not a combination, this is a permutation. So remember from yesterday, if it's a permutation, we can use our NPR button where we've got 20 people. Permutations, I think, placing them 2 at a time. So how many ways are there to place 2 people at captain and equipment manager? That's 20p2. But remember, the permutations can also be done with the counting principle, where I've got how many choices for my captain. Well, I got 20 people to pick from. Then how many people do I have for my equipment manager? Well, there's 19 left to pick from. So whether I do 20p2 or 20 times 19, I'm going to get the same answer. And I just want to show you real quick that that's true. So 20 math over to the probability, NPR, placing 2 at a time, and then 20 times 19, which I think was a lot quicker, but it's up to you. So permutations can be done with the counting principle. Combinations cannot be done with the counting principle. Okay, let's go back to our 20-person track team. Let's say I need 3 co-captains. How many ways are there to pick these 3 people? Well, think about 3 people. If they're all co-captains, I'll pick 3 people. Doesn't matter who. If I switch them around, they all still have the same title. I'm a co-captain with the other 2 people. So this is an example where the order does not matter. This has to be done with our combination button. So we've got 20, choosing 3 people at a time. So the total number of ways to do that, 20, choosing 3 at a time, I've got 1,140 different options with my 20-person track team to pick out 3 co-captains. Okay, number 2. 6 people meet and shake hands. So everybody's got to shake hands with every other person there. How many handshakes are going to take place? Well, really, I'm just asking to shake hands. I'm pairing up the people. I need to know how many ways there are to pair up two people out of these 6. So does order matter here? Well, no, because once I shake a hand with someone, I'm done. If I flip them around, I'm not going to shake hands again because that's still the same 2 people shaking hands. So this is a combination. So it would be 6 choosing 2 at a time. So 6 and 15. There's going to be 15 handshakes if everybody shakes each other's hand 1 time. Okay. So it's all about deciding whether to use the permutation or combination. Number 3. Okay, we're going to go to a ice cream parlor, 31 flavors of ice cream. You're going to buy 2 scoops. Two different flavors. How many options are there for you? How many flavor combinations? Well, I kind of give the word away there. How many flavor, I guess I'll go combos, are there? So again, does a chocolate scoop and a vanilla scoop, is that different if I do vanilla first and then chocolate? No, I still got the same 2 flavors of ice cream. The order does not matter. So this is a 31. Choose 2 flavors. And you will get 465 different options. Okay, let's go with our deck of cards. How many 5-card hands can be dealt from a deck of cards? So how many 5-card hands exist? So we got to first decide if this is an order matters. So think about getting 5 cards. Does the order I get them make it a different hand? If I rearrange the cards in my hand, is it a different hand that I'm dealt? Absolutely not. So the order does not matter. I just want to know how many different sets of 5 there are in a deck of cards. So this is a combination. So there are 52 total cards. We are choosing 5 at a time. And if you do 52, choose 5, there are over 2,598,960 different card hands that exist. I'm going to double check that. That's because my number's a little messed up on my notes here. 2598960. Okay. All right. Number 5. We have a jury pool where they've called in 30 people. We're going to select 6 people to sit on the jury. How many different jury options are there? Well, think about the 6 people sitting down. If I switch the order of them, is that a different jury? And the answer is no. It's the same 6 people that are going to determine guilty or innocent. So we will go with a combination. Split 30, choose 6. Which I don't have the answer. Choose 6. 593,775. Okay, done with the easy ones. Let's throw some twists in here, make them a little more challenging. Number 6. So, there's a jury pool that is consisting of 15 men and 10 women that were called in. What's the probability? Oh, no, not probability. You have to pick 3 men and 3 women for the jury. How many ways are there to do this? So, notice the word and. And tells me to, in probabilities, tells me to multiply. Same thing here when I'm finding how many ways there are to do things. So I need to know how many ways there are to pick 3 men. So I'm just labeling this dash here. This is going to be my ways to get 3 men. My events. You can see I'm labeling my events under this line here. And I want to know how many ways there are to get 3 women from the pool. So if I think about the men, there's 15 men to pick from. I need 3 men. And again, the order doesn't matter because they're all just sitting on the jury. They're all equal in importance. So this will be 15 C3. And then how many ways are there to get 3 women? Well, there's 10 to pick from. How many different ways can I choose 3 out of those 10? That's 10. Choose 3. You gotta think about this as a tree diagram. However many branches this is for the men, different outcomes, off of each one of those, I've got that many for the women. That's why it's a multiply situation. It's like making a tree diagram for my 2 events. So, 15 C3 multiplied by 10 C3. 54,600 different juries. Okay. I think I need a little more room. Did I have that on there? Make sure we've got that. Yeah. Okay, number 7. Okay, we're going to go to the sub shop. In this sub shop, there are 6 meats to choose from, 5 cheese options, 10 vegetable options, 4 dressings, and 3 breads to pick from. And you're going to make a sub, or pick a sub. Your sub will have 1 bread, 3 meats, 1 cheese, 4 vegetables, and 1 dressing. How many of this type of sub can you make? Okay, so think of each of these as events. You've got to have 1 bread, and 3 meats, and 1 cheese, and 4 vegetables, and 1 dressing. Anytime you say the word and, you're going to be multiplying. So I'm going to write down those 1, 2, 3, 4, 5 events. Here's my bread. 3 meats. 1 cheese. 4 vegetables. And then the 1 dressing. And it's how many ways there are to do each one of these. Well, breads, there's 3 breads. I'm going to pick one. That's 3 different options. Or 3, choose 1, but it's just 3 options. When you're only picking 1, you know how many options you have. Here, I need 3 meats. And the order I put the meat on doesn't matter. This is a combination. So I need to know how many ways there are to pick 3 meats out of the 6 available. That's just a 6. Choose 3. 1 cheese, so how many options? There are 5 cheeses, I've got 5 options. Or 5, choose 1 if you want. 4 vegetables out of the 10, so I need to know how many ways there are to pick 4 out of these 10. 10, C4. And on the dressing, there are 4 dressings, so I have 4 options. It's multiply all of that together. One big line on the calculator. Should you type that in correctly, you will get 252,000 different subs that have 1 bread, 3 meats, 1 cheese, 4 vegetables, and 1 dressing. Alright, the last little step we're going to make is to tie this counting stuff in with our probability. We're going to marry the two together in the last two examples. So number 8, we're going to be dealing out 4 cards. So the first thing I want to know is how many 4-card hands exist. And again, we've already established that the order I get them in doesn't make a difference, so this is a combination. So that's 52C4. I'm not even bothered with the total right now. Okay, next question. How many 4-card hands are all face cards? So I'm asking of all of the face cards, remember face cards actually have the face, those are your jacks, queens, and kings, how many hands exist where I get 4 cards that all have a face on them? So I need to know first, how many total face cards are there? So the total face cards would be jacks, queens, and kings of the 4 different suits. So that means there are 12 face cards total. So now I'm asking, well, how many ways are there to get a set of 4? Well, that just means I can find that by doing 12C4. It's all face cards, choosing 4 at a time. So now I can ask a question like, find the probability of being dealt four face cards. Well, my sample space is this first one. It's all possible 4-card hands. And my events that match are the ones that just have the face cards. So I really just have to divide 12C4 by 52C4. And I will show you that. 12C4 divided by 52C4. So not even close to a 1% chance. 0.00183. We'll go with 3 sig figs. Okay. Continuing on with our cards. Part D. Can you find the probability of being dealt no face cards? When you're dealt 4 cards. So again, my sample space is still using the whole deck. So my sample space is the 52C4. Now I need to know, well, how many ways are there to get no face cards when I'm dealt the 4? So I need the total number of no face cards. Well, if you think about it, 12 of the cards were face cards. There's 52 total, so there are 52 minus 12, 40 cards that have no face on them. Those would be your ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, through the 4 suits. There are 40 of those, so this would be 40 choosing sets of 4. And typing that in correctly, 0.34. 34% chance of not being dealt a face card. can you find the probability of being dealt 4 aces when you're dealt 4 cards? It should be pretty small. Well, again, my sample space is not going to change. It's still the whole deck choosing 4 cards at a time. So out of that total, how many of those hands are going to have 4 aces? Well, this is kind of common sense. There's only going to be one hand that has 4 aces. Or think of it as 4C4. 4 aces, choosing 4 at a time. There's only one set of 4 that's going to resist. So it's 1 out of 52C4, which comes out nice, small, scientific, 3.7 times 10 to the negative 6. And the last card example, can you find the probability of being dealt, the probability of getting a 4 of a kind? Again, sample space, 52C4. But now how many 4 of a kind hands are there? In common sense, there's one hand with 4 aces, one with 4 twos, one with 4 threes, one with 4 fours, one with 4 fives, one with 4 sixes, 4 sevens, 4 eights, 4 nines, 4 tens, 4 jacks, 4 queens, 4 kings. 13. So there are 13 hands out of that total. And again, very small, but bigger than that one. 4.8 times 10 to the negative 5th. Alright. Last one, we're at the top of the mountain in terms of difficulty, I think. Let's say now you are going to be dealing out 5 cards. 5 card hands, because that's typically what you're going to get. And I'm going to be asking some probability questions, so we're going to want our sample space. So the first question I'm going to ask is, how many 5 card hands are there? Well, again, should be getting pretty easy. Oh, I don't want that total yet. Let's pretend that that's our total. Now I'm going to ask some probability. What's the probability of getting 1 ace and 4 kings? Okay. So, my bottom number, got it, 52C5. Top number, I've got 2 events happening and they're connected with the word and. So my events are getting 1 ace, and then I want to get 4 kings. Well, how many different options are there for getting an ace? Well, there are 4 different options there. I can get the ace of hearts, the ace of diamonds, the ace of spades, the ace of clubs. There's 4 options. I don't need a NPR or NCR for this. How many ways are there to get 4 kings? There's only one set of 4 kings in there, so there's only one. So it's going to be 4 times 1, or 4, divided by that total, which comes out 1.5 times 10 to the negative 6. Okay, and then our last one, what's the probability of being dealt 4 aces when you're dealt 4 cards? Or, excuse me, 5 cards. 4 aces, but you're still being dealt 5 cards. So, here I gave you exactly what the 5 cards had to be. Here I'm telling you need 4 aces, but I'm still getting dealt a 5th card. But there's no restrictions on it. So, again, sample space, 52C5, but I still have 2 events. I want to get 4 aces, and then I want 1 other card. Okay, being dealt 4 aces. How many sets of 4 aces exist? There's only one. How many other cards are there that I could be dealt? Well, if I got the 4 aces, there's 52 cards in the deck. 52 minus 4 is going to give me 48 other cards. So there are 48 hands that will have a 4 of aces. Excuse me, that will have 4 aces. So it's 48 divided by 52C5. Which comes out 1.85 times 10 to the negative 5th. Okay, that's it.